Hello class, this is section 1.2. In this video, we are going to discuss some basic definitions for the heat problem. The heat problem concerns the flow of heat in a one-dimensional iron rod. For simplicity, we are just going to assume that the cross-sectional area of the rod is 1 meter squared. The book does not assume this. The book assumes that the cross-sectional area is a meter squared. All this does really is add some annoying constants to the problem, so we're just going to simplify things and make it one. So the rod is laid horizontally, like so, across the x-axis. The first definition we should introduce is that of the energy density. It's usually denoted E of x of t. So remember that x is the x-axis and our rod is horizontal. So x tells you where in the rod you're concerned with. T is time, of course, and we're concerned about how heat flows through time. Conventionally, t equals 0 refers to the start of the experiment, and we let time pass and we see how the heat flows. We use energy density because, as you remember, heat is a form of energy. This energy density ext tells us how much energy there is per unit volume of the rod. So ext is the amount of energy per unit volume. Its unit in the SI unit scheme is joules per meter cubed. So it tells you if you have one cubic meter of iron rod, how much energy is contained within it. So if you have a 0, say, there's no energy in the rod at all at that location. If your ext is 10, it means that every cubic meter of the rod around that location x and around that time t has 10 joules of energy. The second definition we want to introduce is the heat flux, or energy flux. It is denoted as a Greek letter phi and has arguments x and t as well. So what phi xt tells you is at that location x and at the time t, how quickly is energy moving to the right per unit area. So for this class, I am just going to always make the cross-sectional area 1 meter squared. However, if that's not the case, if you have a slightly thicker rod, let's say the one where the cross-sectional area is 3 meters squared, you have to remember to divide your heat flux by the area, so you would divide by 3 in that case. The SI unit is joules per second per meter squared. And when phi is positive, this means that you have, at that location x and at the time t, heat energy flowing to the right. If phi is negative, that simply means that the heat energy is instead flowing to the left. And if the magnitude of phi is large, if phi is a large positive or a large negative number, it means that the heat energy is flowing very, very quickly. Now, something that students might get a bit confused about is that phi is a rate. Even though we are not writing phi as a derivative, it is a rate. It tells you how much energy is flowing per second. One other thing to remember is that flux depends on x and t, so it's a local property, not a global property. So the heat is never flowing across the rod at the same rate at every position at every time. So the rate of heat flow changes at the location at the time, and that's why phi depends on x and on t. Lastly, we want to define the internal energy, which is represented by Q, again with arguments x and t. So Qxt is the heat energy generated inside the rod per unit volume and every second. So this means this tells you how much energy the rod is creating every second. Now this might seem a bit strange, but in some physical applications, you want to consider that chemical reactions might cause the rod itself to generate heat, and this Qxt will represent that. But in the beginning part of this course, and most of the problems we'll think about, Qxt will be 0. We will not think of the cases where the rod is magically generating heat. So clearly, the SI unit here should be joules per cubic meter per second. We'll also want to consider integrals of E and Q and talk about what they mean. So remember that ext is an energy density. It tells you how much energy is contained per unit volume of the rod. Now you may remember that there was a formula in physics that told you how to calculate the mass of an object given the mass density, and you would take the mass density and you integrate it. Now the same principle applies here. To figure out how much energy there is between location x equals a and x equals b of the rod, you simply take the definite integral with boundaries a and b, and this tells you how much energy there is in the rod. So you integrate the energy density that tells you how much energy that you have in the rod. Similarly, if you integrate q(xt), this tells you how much energy the rod generates every second between x equals a and x equals b. Now here is one way to convince yourself that this makes sense. So just draw the graph of ext. The x-axis is in meters, but it's really in meters cubic meters, because remember the cross-sectional area of the rod is 1 meter squared. So every x unit of the rod, if you travel vertically, you're actually covering one unit volume of the rod rather than just 1 meter of the rod. So every meter of the rod corresponds to 1 unit volume. And the y-axis is going to be joules per meter cube. That's because that's what density is. ext is density, it's the amount of energy per unit volume, so the unit is joules per meters cube. So remember that an integral is simply the area under the curve. We draw the graph of ext like so, and we mark off the points a and b on the x-axis. So the definite integral e with boundary values a and b is simply the area under that curve. And you see, if you multiply the x-axis unit with meter cube with the y-axis unit, joules per meter cube, you get joules, which is the unit of energy. And it's consistent with the assertion that that integral is the amount of energy in the rod between a and b.